All right, moving to the remaining two examples here. We got to edit this one a little bit because I tried to do something fancy with it, and it just fell all apart on me here. So basically, if you take your pen, just cross out this line here, the frictional force measured, blah, blah, blah. We're going to get rid of that altogether, and we're just going to determine the acceleration. I originally was trying to get something set up that when I realized worked it out previous year with the class, I realized it just was not a very good question. So this emphasizes the point for me anyway. So we have a 10 kilogram brick. We're pulling it along the bench with a constant force of 4 newtons. It's observed to move 2 meters in 8 seconds. Determine acceleration. So the information that's given, we know our mass. So mass is 10 kilograms. We know that the force is 4 newtons, and the assumption here, and I make it a little bit more clear on tests for sure, that's the unbalanced force, and it's observed to move delta D equals 2 meters, and I'm going to say right, and the time for that to occur was 8 seconds. So I list all my information when I'm doing this decoding. I know I want to determine acceleration, and one of the giveaways here is when I have mass, I know it's going to be the FU equals MA. So that force was to the right, and it still doesn't clean up my question anyway. But anyway, we'll just settle it like this, that our acceleration here was 10, so 0.4 meters per second squared. Write it the other way. Acceleration equals 0.4 meters per second squared, and that is to the right. So what I was trying to emphasize in this example is that you can use in the grade 12 course, there may come a time and place where you can go ahead and you can use force to determine an unknown, or and you could be able to use kinematics here. So for example, we could have used the delta D equals V1 delta T plus 1/2 a delta T squared. Actually, we can even go simpler than that. Don't write that down because we even know, do we know final velocity? No, we need the displacement. I'm sorry. So anyway, we'll leave that up there. And we can find our acceleration from that particular question, because we would assume that the brick started with a V1 of 0 meters per second. So it is possible then to go through. Now the numbers, I tried to pull them out of my head, so the acceleration doesn't match when we do it that way. But my emphasis is we have two methods. Solve problems. We can look at it from a force perspective. So from force, or F equals ma, and from kinematics. And what we're doing in this particular unit then is we're combining them together, and that when we combine force and kinematics together, that's where the term dynamics come from. So it's that combination. All right, on to the final example, which does work. We have an ice skater pulling 3 small children with a rope. So I better draw this out. So here are my 3 children and my ice skater, one behind the other. Mass is 25, so I assume it's in the order given, 25, 31, 35. Determine the total force applied to the train of children. So they're connected with a rope. If they reach a speed of 3.5 meters per second, so they are going to have a final velocity, 3.5 meters per second, and I have it going to the right. Time, it's 15 seconds. And we want to find the tension in the ropes, So first thing, we're assuming that initial velocity, she's starting from, or V1, is 0 meters per second, right? So we need to find the acceleration for the entire system here, okay? So We'll do acceleration first. So what do I know? Again, you're just decoding the information. I've got V1, V2, and T. So I can pick the correct formula from that. A delta T. So I know we're going to go 3.50 plus our acceleration multiplied by 15 seconds. So dividing both sides by the 15, we get 0.23 meters per second squared. So that answers the acceleration question. But we want to find tension in the ropes. Now, tension in the rope comes from, it's a force. So we start to look at tension in rope. So what we got to do is we got to kind of move from the entire system down to each individual person. We know the acceleration, all right, is 0.23. So therefore, the entire system, I'm going to call it a system, the entire system has an acceleration of 0.23 meters per second squared. That is to the right. All right. So that being said, we now are looking at determining the force. So the force that that the person requires to move them is really the tension in rope 1. So I'm going to call that T1, T2, and T3. So the force or tension in T1, all right, so that's for the entire system. So whatever the ice skater is pulling at is all going into that first rope. So Fu equals Ma. So we're looking at the entire system. So that unbalanced force is causing acceleration, which would be our tension. So we're on ice, so that's why we're ignoring friction here. So our unbalanced force is the tension in the rope. Mass of the system. So you're looking at the 3 individuals that that skater is pulling. So 25 plus 31 plus 35. And we're going to multiply it by that acceleration, so times 0.23. And what that will do is that will give us the applied force or the unbalanced force in that first rope. All right, so there is your tension or the amount of force in rope 1. So therefore, the first rope has a tension of 21 newtons. Now those 2 subsequent ropes are required to pull less and less. So when we look at the second rope in my diagram there, same idea, we're starting with Fu ma. I know that the acceleration is still 0.23. Everyone has to be accelerating at the same amount because ropes we're not allowing them to stretch. So that means that what's changing then? Well, it's the mass. That second rope is only carrying the 31 kilogram child and the 35 kilogram child. So you'd have your 66 times 0.23. So it's no longer carrying that third child. It's attached to the third child. So 66 times 0.23. So the tension in that next rope is only 15.2 newtons. All right. And the third and final rope then, so T3, so it's the tension in rope 3. And when you look at rope 3, it's only carrying the 35 kilogram mass or the last child. So multiply that 35 by 0.23 and we get 8.1 newtons. So the tension in the ropes decreases as we go down the line here. So there are your 3 tensions. All right, so there is the assigned homework for this next section. Important to go through and take a look at those 11 questions because each one's a little bit different in each case, and it is it's combining our Fu equals ma with our kinematics. So very important that we have a clear understanding of that. So good luck. If you have questions in class, make sure you ask and we'll get them clarified.